So without further ado, I'm going to pass over to Will Hart, who is a PhD student at the University of Oxford, and he's actually my PhD student, so it's great to introduce him. And he's been doing some excellent work throughout the pandemic, looking at estimating the generation time for SARS-CoV-2 in different settings. So I'll pass over to Will, and I've been sort of reliably informed that slides will just appear and they just have done, so that's absolutely fantastic. So yeah, so I'll pass over to Will if you'd just like to unmute yourself and take it away. And then one final thing actually is that after 15 minutes, I'll just give you a quick heads up. So if you could then start to wrap up after that, so that we've got time for a question or two at the end. Great, over to Will.
Great, hello. Give me a shout if you can't hear me. But yeah, thanks Robin for introducing me. And yeah, thank you for the invitation to speak. So I said I'd speak for a little bit about changes in the SARS-CoV-2 generation time. Ooh, I can't. There we go. So yeah, so just as a quick overview of what I thought I'd talk about. So firstly, I thought I'd just sort of run through a bit of stuff about the methods we might use to estimate the generation time, and specifically how we can estimate it using data from source recipient or infector-infectee transmission pairs. And then after that, I'm first going to talk about some work sort of implementing these methods and applying it to data collected early on in the pandemic. And then finally, I'm going to talk about applications of the same models once they're adapted to some data from UK households from later on in the pandemic and seeing how the generation time seemed to change over time. And finally, I guess I'll end with some conclusions. Okay, so firstly, in terms of methods for estimating the generation time, I've put on a slide up that's possibly fairly similar to what Julia showed us earlier, but just to run over the idea again, we've essentially, in a transmission pair, we've got an infector who I've here called patient 1 and an infectee here called patient 2. So we're just going to assume that we know which one's the infector and which one's the infectee. And then, so at some point, the infector is going to develop symptoms, and then at another point, either before or after they develop symptoms, the infector is then going to infect the infectee, patient 2. So in general, for a transmission pair like this, we assume that we're able to observe the serial interval. So again, that's the time between the infector and the infectee developing symptoms. So of course, in reality, there may be some ambiguity about whether symptoms actually start, but we're not going to really get into that. And so the problem we're sort of left with is we know the serial intervals, so we know when the two develop symptoms. And then at best, we might have some partial information about when they become infected. So we might know that one of the infector or infectee was exposed during a certain time interval, let's say. So then sort of the mathematical challenge is then, given this data, how can we back infer the generation time? And so to do this, somewhere along the way, we're going to have to make some assumptions. And really the big thing we're going to need to assume is how infectiousness depends on symptoms, or how symptoms depend on infectiousness. Okay, so here I'm going to focus on two particular models. So this first one on the left, I've called the independent transmission and symptoms model. So I'll come to it in a bit why I've called it that, but the main assumption here is that the generation time is independent of the incubation period of the infector. And so why I've called it independent transmission and symptoms is just simply because if you think about the probability density function of the generation time, that's essentially telling you how likely you are to pass the virus on at some given time since infection. So in other words, this PDF of the generation time is essentially telling you your average infectiousness, or your sort of relative infectiousness, at least on average, at each time since infection. So this assumption that the generation time and incubation period are independent is essentially saying that transmission is independent from symptoms. So clearly this is quite a basic assumption and probably fairly unrealistic. So for example, in reality, there's probably going to be some relationship between your viral load and whether you're showing any symptoms. And another big one is just behavioral factors are clearly going to be affected quite a lot by whether you're symptomatic or not. So even though this is a fairly basic, crude assumption, is actually very common, and particularly in studies where the generation time for SARS-CoV-2 has been estimated before, it's been extremely widespread. So that's the first model. And then the second model on the right was the model that we sort of developed to try and provide an alternative, and hopefully a better alternative to this first model. So in this second case, we're going to take a so-called mechanistic approach, which is sort of based on compartmental modeling. So the idea here is that we break down infection into 3 stages. So first of all, you've got this latent period, and then you've got some sort of pre-symptomatic infectious stage. And then finally, you've got a symptomatic infectious stage. So the idea here is that with this model, infectiousness and symptoms can be explicitly linked. So in particular, pre-symptomatic and symptomatic infectious hosts are going to be assumed to have different infectiousness rates. And so then when we fit this model to data, we can estimate the relative infectiousness of pre-symptomatic and symptomatic infectious hosts. So we've got these 2 models, and the nice thing about them is they're both just about straightforward enough that under both models, we can derive some expressions both for the generation time and the serial interval. And then also, given some observed data from transmission pairs, we can write down some likelihood of that data for each model. Okay, so now we have these methods. We first applied them to some existing data taken very early on in the pandemic. So this was data mostly from Asian countries that was previously collated from a few different studies by Ferretti and co-authors in a preprint. Okay, so fitting these 2 models to data, we then estimated 3 distributions. So on the left, we've got the generation time. On the right, we've got the time between showing symptoms and transmission. And so the density function of this is essentially telling you how infectious you are relative to when you show symptoms. And then on the right, we've got the serial interval. So then comparing the predicted serial intervals on the right to the observed data, we can then see that the mechanistic model gave us quite a significantly improved fit compared to the standard well-used model in which we assume that transmission and symptoms are independent. And then on the left, in terms of the generation times, actually there's not too much difference between our independent transmission and symptoms model and the mechanistic model. So in particular, the means are fairly similar, possibly a slightly longer tail of infectiousness for the mechanistic model, but not particular difference. Is really this curve in the middle where you can really see a big difference between models, where for the mechanistic model, we've got this distribution of infectiousness that's really concentrated around the time of symptom onset. And so you can see there that there's a sort of a discontinuity in the profile for the mechanistic model. And this is really just arising as a result of the compartmental structure. But also we can sort of attribute it to behavioral responses when someone starts showing symptoms and maybe then decides to stay at home. Okay, so just summarizing in terms of the actual generation time estimates. So these estimates for the independent transmission and symptoms model were fairly similar to other estimates from similar time points in the pandemic, and also obtained using this same crucial assumption. Whereas for the mechanistic model, we got a slightly higher but fairly similar mean estimate for the generation time, and then a bit of a higher standard deviation, but still sort of within the same ballpark of other estimates with this independent transmission and symptoms assumption. And so one other thing that was interesting that came about when we fitted these 2 models to the data was that we actually got quite a big difference in predictions for how many transmissions are occurring before symptom onset. So when we assumed independent transmission and symptoms, we estimated about half of transmissions occurred before symptoms. So here we're not including asymptomatic infectors. So if you include the possibility that people could be asymptomatic, then sort of the total non-symptomatic portion of transmissions would be higher. But we got about 50% with this first model, which was sort of in line with a lot of other estimates. Whereas using the mechanistic model, we estimated a much higher proportion of pre-symptomatic transmissions, so around 65%. And so what this really showed us is that possibly, whereas obviously we need to put in place measures to stop transmission from symptomatic hosts, really the big effect can be had by actually contact tracing and trying to find pre-symptomatic contacts. Okay, and then so obviously all this came from data collected very early in the pandemic. So we then sought to try and update our estimates using some more recent data. So we did this using some data from a household study carried out in the UK by Public Health England between March and November last year. And because we were now using household data, we needed to adapt our methods somewhat. So there are sort of some intricacies for household data that you don't really get when you're just looking at transmission pairs. So the big one is that you don't really know the chain of transmission within a household. So you've got household members showing symptoms at different points, but you're not always completely sure who's infected who. And another big one is just the fact that household contacts are going to be much more regular, much more frequent than contacts, say, in the community. And so the way we got around this was to use a data augmentation MCMC approach, fairly similar to approaches that have previously been used for flu. Okay, so here are some of the results we got. So the violin plots here are just showing us sort of posterior distributions, first for the mean generation time, then for the standard deviation, and then for the proportion of pre-symptomatic transmissions. So in terms of the mean generation time, we get sort of about 4 days with independent transmission and symptoms, but then a higher estimate now under the mechanistic model, more like 6 days. So these two estimates were still fairly consistent with our estimates from earlier on in the pandemic, so maybe slightly shorter than our earlier estimate with this standard independent transmission and symptoms models. But what was really interesting was the much higher standard deviation for both models compared to earlier on in the pandemic. And so I'll come back to this in a bit, but sort of one immediate thought we had when we found this was this could have something to do with different isolation policies in the UK compared to the Asian countries where our earlier estimates came from. So in particular, when you only have home isolation compared to sort of hotel isolation, you might expect sort of a longer tailed infectiousness distribution, which is giving us this higher standard deviation. And so, yeah, so here again are just the point estimates summarized. So I'll just move on, I think. And so what I've plotted here is that, again, these distributions using the point estimates of the generation time, this time from onset of symptoms to transmission, and the serial interval on the right. So with this UK data, we now see a really stark difference in these estimated generation times for the two models. And so possibly with this unrealistic assumption of independent transmission and symptoms, we then end up with a fairly unrealistic looking distribution that seems to peak extremely early in infection. But on the right now, the serial intervals predicted by these two models are actually fairly similar. And because, again, with household data, we don't know sort of the exact chain of transmission, there's no sort of easy comparison to data we can have, but certainly these similar serial intervals suggest that these two models are actually, in this case, giving a fairly similar fit to the data that we can't. So it's not to say that one model's better than the other, or that the models are equally good, just that we can't really tell apart which one's better based on this household data. But what was really interesting was when we then split up our estimates, and instead of just fitting to the whole data set, we started to consider data from different time periods individually. And so what we then found was, whereas between March and April and between May and August, there was a fairly similar mean generation time, so about 5 days, which was again consistent with sort of studies from earlier in the pandemic outside of the UK. We then found a massive drop off in the mean generation time from September to November. And then I've just shown these standard deviations as well. So you see a similar trend, but so interestingly, both of these are sort of under the 5 days we got for the whole combined data set. So it seems that sort of the high standard deviation might partly be because we're sort of combining data with quite different means, which is sort of leading to the standard deviation that we're estimating being inflated. So yeah, so that figure back there was when we assumed independent transmission and symptoms. But in fact, when we looked with the other model as well, we found this same trend of a lower generation time between September and November 2020. So the natural question there was to ask, well, why does this change in the generation time take place? And so obviously the alpha variant started to spread around that time. But in fact, through sort of genomic sequencing, we found that that wasn't really the case. It was only present in 2 households. So we think that this decrease in the generation time was mostly behavioral. So one idea was that it could just be to do with sort of in winter months, people mixing more indoors, leading to shorter generation times. Okay, so
well, that was 15 minutes, just say it was 15 minutes. So if you could wrap up in the next minute or two, that would be ideal.
Perfect. I think I'm hopefully just about on time, just wrapping up now. So I guess 2 main conclusions from what I've said. Firstly, we've seen that estimates of the generation time can be quite sensitive to modeling assumptions. So we've got to consider certain factors when we're going to decide which model to use, which estimates to take forward. So one would be sort of plausibility of the different models, but also when we're taking these forward, say if we're using these estimates for models that estimate the reproduction number, we find that such models estimating the reproduction number sometimes reproduce this assumption of independent transmission and symptoms. So maybe in that case, that estimate might be better. And then our other finding that the generation time was changing really just shows the importance of continued estimation over time, particularly in the face of new variants, and particularly because so many of the estimates still being used are from right at the start of the pandemic. Okay, so yeah, thanks very much. I just wanted to say thank you to my supervisors, Robin and Philip, and also our collaborators at the London School and at Public Health England.
Thanks very much, Will. That was great. And as you said, perfect timing, so that's especially good. So thanks very much for that. So we have a couple of questions that have just come in. So the first one is to do with the fit of the mechanistic model to the early data from the pandemic, so the sort of combined data set that Ferretti et al. Put together. And the question is about how you conclude that a better fit to the serial interval reflects the linkage to the time of symptom onset, rather than some sort of rather than recall bias that's present in the data. Yes, do you have any thoughts on that, please?
Yeah, it's interesting. I guess it's really impossible to tell. So I don't really know if the recall bias would go one way or the other. So in principle, you could try and account for this, but I don't have a feeling for sort of recall bias, like particularly taking things one way or the other and favoring one model or the other model. So really, we were just giving symptom onset dates and we had to go with them essentially. And so what we had indicated a better fit for our model. But sure, once you take account of biases, it might change things around, but we've got sort of no indication.
Great, thanks very much. And the next question is from Songmok Jung from Kyoto University, and he has asked, so just to summarize the question, essentially your estimates derive from household data, and how reflective are your estimates of generation times for sort of spread within the community?
Yeah, of course. So I guess the answer is really, it's hard to tell. So all we can do is compare our estimates for other estimates from the community. And I guess the problem is there aren't very many of those, at least not since the first couple of months of the pandemic. So of course, like we can correct for some stuff within households, but other things, say sort of transmission in households after people are self-isolating, we can't really account for. So we might expect sort of a longer tail distribution for transmission in the households, but really without other estimates there, all we can do is just compare to what was there from very early in the pandemic.
Great, sounds good. Thanks very much, Will. That was excellent, and like you said, we're bang on time. So yeah, thanks very much for an interesting talk.